At this point, looking at the original objective, we've now defined two of the four backpropagation equations, equation 3 and equation 4. Equation 3 was the partial derivative of the cost function with respect to any arbitrary weight parameter in our network, whereas equation 4 was the partial derivative of the cost function with respect to any bias parameter. We define these equations in terms of delta parameters, which we can generalize as follows. We have that the delta term for a given neuron in some arbitrary layer L is equal to this expression if the neuron is at the output layer, and this expression if the neuron is at some hidden layer. Now the first two equations are really just vectorizations of these delta formulas. Hence, moving from this piecewise function to matrix vector notation becomes the last piece of the puzzle. And since the cost function partial derivatives are defined in terms of these delta terms, we are required to first compute these delta terms. And say we'd like to do it in bulk as opposed to one by one in order to improve the efficiency. What we can do is we can start at the output layer and compute a vector which contains as entries all the delta terms for the neurons at the output layer. So we can define the following vector which contains the delta entries for neurons at the output layer. So the first entry would be the delta term for the first neuron in the output layer, all the way down to the delta term for the nth neuron, the output layer. And we see from the delta formula that delta terms for neurons at the output layer is given by this expression. So we can write this vector as follows, where the delta term for neuron 1 is given by this expression, and the delta term for neuron n is given by this expression. Now the entries here are just products of two different derivatives, and so we can represent this entire vector as a Hadamard product of two individual vectors. And just for clarity, the Hadamard product, well, let's say, is some vector x1 all the way to xn, and the Hadamard product is denoted using this symbol. So if we take the Hadamard product of these two vectors, we simply get a vector where the entries in the resulting vector are just products of the entries in the operand vectors. So this would be x1, y1, all the way down to xn, yn. So we can represent this entire vector as follows. We have the vector containing the partial derivative of the cost function with respect to activations. And we take the Hadamard product with a vector containing the derivatives of the activations with respect to their weighted inputs. So this would be. Now for completion, we're going to introduce some additional notation. Recall that for some activation in some neuron I in an arbitrary layer L, this was given by some function, which we refer to as the activation function, applied to the weighted input of this neuron. And so when we differentiate the activation in terms of its weighted input, we could also denote this derivative as follows, using this sort of notation. And that's what we're going to do now for the entries of this vector. So we can rewrite this vector as, we have that the first entry is given by the derivative in terms of the weighted input at neuron 1. And for neuron n, we have the derivative in terms of the weighted input at neuron n. Now, the first vector has a special meaning, and this vector is in fact the gradient of the cost function in terms of the activations. Recall that the entire purpose of backpropagation was to compute the gradient of C with respect to the network parameters. This is not to be confused with the gradient of C in terms of the activations, which is what we have here. Now, as for the second vector, this vector can be represented as follows. We can take this entire vector and state that this is equal to the derivative of the activation function applied to the vector containing the weighted inputs for the neurons in the output layer. So this would be Z1L all the way down to ZNL. So if we take this function and just apply it to the entire vector, we get this vector as an output. If we just write this vector more compactly as ZL, that is the vector containing the weighted inputs at neuron L, we end up with the activation function applied to this vector ZL. And so the delta term vector at the output layer can be represented as the gradient of the cost function with respect to the activation and its Hadamard product with the derivative of the activation function applied to the weighted input vector. And if we write the original vector more compactly as just delta L, that is the vector containing the delta terms in the output layer, we get the first backpropagation equation, which is just this expression equal to delta L. Next in line, we can find the delta vector for some arbitrary hidden layer. So for some arbitrary hidden layer, we can define a vector where the first entry is the delta term for the first neuron in this hidden layer given by L, all the way down to the delta term in the nth neuron. And we see from this formula that such a delta term is given by this expression. So we can represent this vector as follows. The first delta term becomes this sum. Notice that we've substituted 1 for j in this formula here. And the delta term at the nth neuron becomes this sum right here. Now expanding out this sum, we see that only the first two terms are defined in terms of the summation variable I. So we can write this vector as this vector. And once again, if we consider that the entries here, for instance, the first entry is a product between this linear combination and this derivative, we can yet again split up this vector into two vectors, which are combined using the Hadamard product, in which case we get the Hadamard product between these two vectors. And just as we used an alternative notation for the activations at the output layer, we can apply the same notation to activations at some arbitrary hidden layer L. So this derivative would then just be given by the derivative of the activation function at layer L applied to the weighted input vector at layer L. Now, as for this vector, we can break it down as follows. Now, this vector can be computed as the product between the following matrix and the following vector. And this vector, as we saw earlier, was a delta term vector. And in this case, it's the delta term vector for layer L plus 1. And so we can write it more compactly as delta L plus 1. Now this matrix has a special meaning, and in order to define it, we're going to revisit some of the theory in the introductory video. Now recall that if we had some activation for some neuron I in layer L plus 1, this activation was given by the activation function for layer L plus 1 applied to the weighted input at the neuron. Now if we want to capture all the activations at layer L plus 1 in a vector, then we can vectorize these activations as A1, L plus 1, all the way to AN, L plus 1. And this vector represents the activations, that is the output from layer L plus 1. And writing this vector out in terms of the weighted input, we get that this is equal to the activation function applied to the following vector. Now this vector can be further broken down into the following matrix vector product. Now this matrix we can represent more compactly as W L plus 1, and this is the matrix containing all the weights going from layer L to layer L plus 1. And in fact, the first row contains all the weights going to neuron 1, and then the second row contains all the weights going to neuron 2, and so on. Now, if we were to take this matrix and transpose it, we get that W L plus 1 transposed is given by the following matrix. And if we look at this matrix and compare it to the matrix we got earlier when deriving the delta terms, we see that this matrix is in fact also W L plus 1 transposed, which means we can rewrite this vector as the transpose of the W L plus 1 matrix multiplied by the delta L plus 1 vector. And so if we backtrack a bit, we saw that this vector could be denoted as follows using the weighted input vector at layer L. And so this entire Hadamard product becomes this vector, which was given by this matrix vector multiplication. And so we have W L plus 1 transposed multiplied by delta L plus 1. And you apply the Hadamard product to the derivative of the activation function applied to the weighted input vector at layer L. And if you go back to our original vector, we can write this vector more compactly as delta L. That is the vector containing all the delta terms at some arbitrary hidden layer L. And therefore we have that delta L, the delta L vector, is given by this formula. And this was in fact the second of the 4 backpropagation equations. And we've now derived all 4 backpropagation equations. In coming videos, we'll see how we can implement backpropagation in conjunction with gradient descent to train a real neural network, and we'll do so in Python. So stay tuned for that. Thank you for watching, and I'll see you in the next videos.